Hi everyone, welcome to IROS. I'm going to talk about our exciting new work on certifiable object pose estimation. While we have seen remarkable progress in developing various kinds of robotic systems, safety has now evolved to be the main bottleneck in taking many of these to the real world deployment. Several unfortunate accidents have brought the issue of safety to fore. The main motivation of this work has been about ensuring safety and adaptivity of perception models in the autonomy stack. So we raised two questions in this work. First, can we certify if an output produced by a robot perception model is correct or not? Second, when the model makes errors, how can we correct for them and learn from it? Classical methods have attempted to answer the first question using data. In this work, we seek a complementary approach. We attempt to use the underlying geometry of the problem being solved to certify the model. If we expand various components of the perception block, uh, it typically looks like this. So it has a distinctive front end that is learning based and a back end that is optimization based. The back end typically attempts to impose some geometric consistencies. What we propose in this work is that to certify the end-to-end perception component and to do self-training and adaptation of the model using such geometric consistency constraint can be crucial. So going back to the two questions, can we certify if an output produced by a robot perception model is correct or not? We propose a notion of a certifiable model, which along with the model implements two certificate checks. The first is observable correctness, which essentially checks the geometric consistency between the input and the output. And the second is a non-degeneracy certificate, which determines if for the given input, the problem has a unique solution. For the second question, we propose a correct certify and self-train strategy that is able to bridge even a large domain gap. In the interest of time, I'm going to focus in this talk only on the second question. So what does the correct certify and self-train strategy do? Let's say we have a model that is suffering from a significant domain gap at test time. The corrector is a differentiable optimization layer that attempts to correct the internal representations of the model so that the model output better aligns with the geometric consistency requirements. The certificate, on the other hand, checks if the output produced indeed meets the pre-specified geometric requirements. The self-training then uses the certified input-output pairs as annotated data to self-train the model. So just to give you an illustration, let's say you have 100 input samples at test time. The model makes prediction on all 100 of them. The corrector further helps the model improve upon those predictions. So you have 100 improved predictions, but we do not yet know which of those corrected outputs are indeed correct and which of them are not. The certifier tells you that. Suppose now the certifier says 30%, there's 30 out of 100 outputs are certifiably correct. The self-training procedure then will use those 30% of the data, input output, as if they are annotated samples and retrain the model. Now, once trained, it'll keep iterating this loop till it starts getting almost all of the test data right. So we apply this strategy on the object pose estimator. It takes in a point cloud and regresses semantic key points. The semantic key points are then used to estimate the object pose by solving a 3D registration problem. Now, the domain gap is going to cause errors in the key point detection. Our corrector attempts to correct the detected key points. This is the visualization of how the corrector works. For the certificate, we stipulate a simple geometric constraint between the input and the observed partial point cloud and the CAD model. The surprising thing that we observe is that even with an initial 10 to 20% certifiable instances, the self-training is able to soon achieve a close to 100% certifiable outputs in a few hundred training iterations. We compare the self-training with various other self-supervised approaches. We show considerable improvement with respect to current state of the art, but more importantly, our self-supervised approach matches with the performance of the fully supervised baseline, which is trained using full annotated data on the test domain. So to conclude, this work enables a self-training pipeline that can adapt a pose estimation model to meet the specific certification requirements. Our recent work has extended this to RGB and RGBD based pose estimators as well.